It's that time of the year again when here in America, people might get a little bit more patriotic as they celebrate their country's independence with a little bit of fireworks. It turns out that fireworks are used by people all over the world in a variety of celebrations. But the question is, how do fireworks work? To answer that, let's start with a little history. Fireworks were invented in China over 1,000 years ago, possibly even 2,000 years ago. According to one legend, a cook dropped some potassium nitrate, also known as saltpeter, into a fire and observed the colorful flames it produced. Sparked by curiosity, he went on to combine the potassium nitrate with charcoal from the fire and sulfur to make the very first form of gunpowder known as black powder. Later, Chinese inventors would take this gunpowder and stuff it into hollow pieces of bamboo. When thrown into a fire or lit, the bamboo stuffed with black powder would explode in much the same way that a modern firecracker does. In fact, the very same recipe is still used today. Black powder is typically made of about 75% saltpeter, that is potassium nitrate, 15% charcoal, which is essentially an impure form of carbon, and 10% sulfur. The explosion of black powder is a complex chemical reaction similar to combustion reactions. Carbon is the main fuel, and sulfur is a secondary fuel that helps the mixture to react more easily and ignite at a lower temperature. The potassium nitrate serves as the oxidant, similar to oxygen in a combustion reaction. However, unlike oxygen, potassium nitrate is a solid that is pre-mixed with the fuels. Because of that, fireworks tend to burn faster than ordinary fires, which depend on oxygen from the air, and fireworks cannot be extinguished by smothering, as ordinary fires can. The main products of the reaction are potassium carbonate, potassium sulfate, carbon dioxide, and nitrogen gas, although there are a number of other minor products too. The reaction is exothermic, that is, the reaction gives off heat, exo meaning out, and thermic meaning heat. The combination of heat and gases produced by the reaction is what gives black powder its power. Gases take up about 1,000 times more space than solids, and heat causes gas to expand even more. When black powder is enclosed in a hard shell, the expanding gases build up pressure until the shell breaks, creating a big boom. When there's a hole allowing them to escape, those expanding gases can propel a firework up into the air. A modern firecracker has two main parts, the shell and the fuse. The shell is simply a container made of a tightly constructed thick paper that functions the same way the original bamboo did. It is filled with black powder or flash powder or some other explosive mixture. A fuse enables fireworks to be safely lit by adding a time delay before detonation. It contains black powder in its core so that it can burn without oxygen. This is surrounded by multiple layers of string or fabric. Nitrocellulose lacquer is applied to hold it together and make it water resistant. Fireworks that light up the sky are a little more complex than firecrackers. They are typically fired out of a tube called a mortar. Let's look inside the mortar tube and place the cross section of a firework inside. The main fuse runs all the way down the tube to the firework. Although you could use a normal black powder fuse to light the firework, it is typically lit with an electric match instead so that a lot of fireworks can all be timed and controlled by a computer. At the end of an electric match, a bridge wire typically made of nichrome gets hot when electricity goes through it. The heat ignites a sensitive mixture of potassium perchlorate and zirconium metal, which react to make potassium chloride and zirconium dioxide. That reaction is very exothermic, and the heat from it in turn lights the firework. The first thing to burn in the firework is the lift charge or propellant, which can be made out of black powder or something similar. The hot nitrogen and carbon dioxide gases produced by the burning black powder propel the firework into the sky. Alternatively, some fireworks do not contain a lift charge and use compressed air to launch them. While the firework is going up, an internal time delay fuse is lit. This enables the firework to reach maximum height before it explodes. The time delay fuse then ignites the burst charge, which typically is also made of black powder. However, if the firework is a salute type, the burst charge contains flash powder instead of black powder. The flash powder results in a bright white flash followed by a much louder bang. Although there are many different flash powder formulations, the most common one is a mixture of potassium perchlorate and aluminum powder, which react exothermically to produce potassium chloride and aluminum oxide. In this reaction, potassium perchlorate is the oxidant, an even more powerful oxidant than potassium nitrate. Aluminum is the fuel. It may seem odd that a metal can be a fuel, but actually metals like aluminum and magnesium are very good fuels and burn at a much higher temperature than black powder. In fact, the super bright flash of a salute is caused by the higher burn temperature of aluminum or magnesium. Okay, now what about the other types of fireworks that form pretty colors and different shapes? Most fireworks also contain a number of additional smaller pieces known as stars. When the burst charge ignites, it blasts the stars in all different directions. Different shapes of fireworks can be formed by arranging the stars in the desired shape. There are many different compositions of stars depending on the color and effect desired, but the basic composition is potassium perchlorate with a polymer and a metal salt. Once again, potassium perchlorate is the oxidant. The polymer functions both as the fuel and as a binder to hold the mixture together. Typical binders are shellac, red gum, PVC, or even starch. The metal salt creates the desired color. For example, red can be made using a strontium salt, such as strontium nitrate. Green can be made using a barium salt, such as barium nitrate. Blue can be made using a copper salt, such as copper 2 chloride. And purple can be made by mixing strontium and copper salts together. But why? Where do the different colors come from? Well, for really small things like electrons, energy is quantized. That is, energy exists in chunks rather than a continuum. The best way to picture this is a little staircase for the electrons. We call the steps energy levels. When an atom absorbs some energy, such as absorbing heat from a blast, one or more electrons can go up to a higher energy level. However, the electron won't stay there forever. It always wants to come back down. And when it comes down, it gives off light. But not just any light. It gives off the color of light corresponding to the drop in energy of going down a step. If the steps are fairly close together, the photon emitted will be a lower energy red light, which is the case for strontium. If the steps are farther away from each other, as is the case for copper, the light emitted will be higher in energy and may appear blue. Keep in mind that this is a simplification, and real electron energy levels are not equally spaced, but this is the gist of what's going on. I hope you enjoyed this video and learned something about fireworks. If so, please share this video with a friend, check me out at ketsbook.com, and in the comments below, please tell me about your most amazing fireworks experience. Although I've seen a lot of nice fireworks displays, the most amazing one was in Beijing in 2005. They had just lifted a 12-year citywide ban on fireworks, and people went crazy. Huge fireworks were literally everywhere in the sky. From the top of my building, you could look in any direction and see nothing but colorful fireworks. The sound was deafening. Some people even shot fireworks out of their apartment windows. Me, I just watched in awe. Have a safe and happy 4th of July.